Okay, so yeah, first things first is that we have like this atom here inside there, and so we can actually just draw some of these other atoms outside here just for reference. There we go. And then at the center here we got like this we got another atom there, and so we know that actually the radius here would be the square root 3. No, wrong. Yeah, I'm correct, it's the square root of 3. So the radius would be equal to square root 3 of the A, which is basically this side here would be A. Good. Just in case that I need it anyways. Which is the close packed direction? The close packed direction here would be this one here. This one here is pretty close packed. This one here is also pretty close packed. Because yeah, all of them is actually touching each other. Which is basically why this guy is that guy. So yeah. So yeah, the direction here would be okay, let's try to write this guy here. In the H direction you go to -1. No, you don't go to negatives. That's what the crystallographers say. So yeah, you put 1 bar because you're going at the negative direction. For the Y, you go into the positive direction, and then for the Z, you go up by 1. That's that. Or you could write that as like, yeah, this guy is in relation to the 110. So yeah, we are just really only looking at this 110 plane. So yeah, 1 bar, 1 bar, 1 bar. So that is another solution. It's 1 bar. So it's 1 bar going inside, 1 bar it's going down, and then 1 bar again going to the backside. So yeah. So yeah, I guess that's a valid answer. No. No, it's not. Why? Because this is not all 1 bars. Instead, it's just 1 bar, 1 bar. Because you're still going in the Y direction. Same thing. Oh wait. But you need to realize another thing is that you could actually go into the opposite direction as well. You could go to 1 bar, 1 bar. You could also go to 1 bar, 1. I think that's all. You go to the -1, then 1, then 1, and then you go to -1, 1, but you go down 1 bar. Yeah. So that's all the answers that I could see. There is obviously some more, but yeah, the bars would. But yeah, so that means that you have like another 8, I believe. So yeah, but yeah, at this point I don't really care. Because yeah, we are only really interested at the 110 plane. So yeah, that's that. C, part C, there we go. Wait, no. Okay. I guess that's that. Okay. C. It is difficult to get 100% pure iron because there are often some impurity elements in the materials. One common impurity element is hydrogen, which is present as an interstitial element in iron. Okay. Circle the image below that accurately shows an interstitial hydrogen atom in the plane 110 plane of iron. Okay. So yeah, the first thing that we need to remember is that for the 110 plane, of a BCC atom is that, yeah, this thing here doesn't touch. So yeah, that thing is not an answer. This guy here is also not an answer. So the only option is this guy or this guy, B or C. And then after that we know that yeah, for and then we know that from a BCC that yeah, the sides wouldn't be like a square, so this thing couldn't be. So we can just cross them out there. So the answer that I'm going to be choosing is B because of its rectangular stuff, and also it has the hydrogen there at the side, not at the center like A. That's that. Okay, so that's that. So now let's actually go to D. Iron has a radius of 1.24 angstroms. Calculate the density of iron in grams per centimeter cubed. Okay, we need to start calculating some stuff. So the first things first that we know is that from a BCC atom, you get two atoms. No, for a BCC structure iron, you would have two atoms per laticites. Wait, really? 1, 2, 3, 4. What? What? 1, 2, 3, 4, 5, 6. Yeah. So yeah, you have two atoms, and then after that, and so we just need to try to find this guy in grams per centimeter cube. But you know what? Let's actually just go ahead and just find the area per latticite first, because obviously that's what I'm going to be doing first. 1.24 angstrom is the initial stuff, but then last time I have already calculated that the A would equal to square root 3 of the radius. It's not A times square root 3, it's A equals to square root T of R. So yeah, that means that last time I just actually calculated that wrong. And so let me just turn on my lights first. Okay, so we will just calculate 1.24, multiply that by the square root of 3. This would get me the angstroms. So multiply that by the square root of 3. This would equal to 2.15 angstroms. Yeah, it's 2.1477, but yeah, obviously I don't. But obviously I'm just only taking like the 2 decimal places behind. But yeah, sometimes only a digit. I know. And so when you have this, we want to convert it first to this first into centimeters. So yeah, that's 2.15 times 10 to the power of negative 8 centimeters. And so when you calculate the volume, this would equal to, just cube the answer, multiply that by 10 to the power of negative 24. There we go. Got 9.91 centimeter cubed. So that's the volume. And so obviously we can just write it into 2 atoms per centimeter cube first. 2 divided by the answer. So what you got is that the density equal to 2.02 times 10 to the power of 23 atoms per centimeter cubed. That would equal to, so yeah, obviously 1 atom would equal to something else. 6.02, so yeah, that guy. So we need to divide it by 6.02 times 10 to the power of 23. That would equal to 0.34 moles per centimeter cubed. So that would equal to, so yeah, basically we need to convert from the mole into grams, which is why we have our periodic table. Iron, that's 26, that's 58, no, 55.845. And so to convert from moles to say it's grams per mole, so yeah, you just need to multiply it. Multiply that by 55.845. What you'll get is equal to 18.72773 grams per centimeter cube. That's the density. But yeah, sometimes that, yeah, you could actually just see the density sometimes. Wait, the structure is BCC, the grid parameters is 2.86, but yeah, I guess that, yeah, each stuff is different, I guess. Now let's see the density because I'm also curious. Let's see, density. Wait, is density at the top? No, density is not at the top. Where is it? Where is it actually? I don't think I can actually see the density anymore. But yeah, I'm still curious. 7.874 grams per centimeter cube. Yeah, I guess that we. Yeah, I guess we could actually just say that to be that. Or maybe my calculation is totally wrong, which is not the case because I'm a genius. I well, let's see. Oh, okay. Multiply by 10 to the power of negative 24. Don't, like, yeah, don't forget about that. That's something critical. So yeah, first things we got 1.24. We multiplied it by square 3 to get the lattice size, I guess. And then you convert that into angstroms, which is multiplied by 10 to the power negative 8. Yeah. And then after that, you turn it into a volume, which is that, and so you just divide the atom per lattice side. So yeah, one lattice side's volume is that. Good. And then after that, you multiply that by the other 6.02 times 10 to the power 23. Yeah, to the power of 23. So yeah, I guess that's correct. And so you'll get 18.73. Yep. I guess that's the answer. Like, yeah, I don't. Well, like, yeah, I don't really care about the math anymore. So yeah, I guess that's that. You Okay, so now let's actually just go into the next question. You decide to run a tensile test on an iron wire. After the experiment, you look at the part of the sample that was deformed and see the following. Okay. Iron wire before applying tensile force. Okay. And then after it, there are planes that is actually deformed. So yeah. In one sentence, explain what is special about this shaded planes. The shaded planes are the densest, are the closely packed planes. And yeah, I don't really know about what is the plane, but yeah, that's that. So yeah, that's the answer. That is called the slip plane anyways. Problem 4. Let's see how long has this thing been. Around 1 hour, good. We have talked a lot about semiconductors, but we haven't mentioned one interesting class of semiconductors. Organic semiconductors. Professor Grossman will be using organic LEDs for horticultural lighting on the spaceship, so it's important to understand them. Okay. So, I guess that's that. Did I? Okay. So yeah, Jeffrey Grossman here. Professor Jeffrey Grossman, I'm so sorry. He is having fun with plants. as he say LDs can be used to grow plants on space. Good. So yeah, one example of an organic semiconductor is polyethylene, PE. A portion of its structure is shown below. Circle the repeating unit. You can actually just see that the you can actually see that there is actually two different types of repeating units. But yeah, I would just circle this one here as the repeating unit. Polyethylene is a semiconductor because of its resonance structures allows electrons to move. One is structure shown above. Draw one repeating unit of another polyethylene structure. Okay. So yeah, I would say that the other structure would be the let me just where's my pen there? This so I would just draw it like this here. And I would say that that's carbon, carbon, hydrogen, hydrogen, there, and then this guy here actually has this double bond here instead, which is what it makes it to have this resonance structure, because it can just change from one thing to another. Modified image of astronaut working in space. Original image is in the public domain. Source NASA. So yeah, I guess that he is pretty good there. To enhance conductivity to useful levels, polyethylene needs to be doped. But dopants behave differently from inorganic semiconductors. When doping with bromine, 2 electrons are removed from the polymer per bromine molecule. So when you so when you put bromine inside it, it takes out 2 electrons. So this would be a p-type because it actually removes. So yeah, it removes electron. There we go. The band gap for neutral polyethylene is shown below. Sketch the band gap for Br2 minus doped polyethylene on the same axis. Okay. So let's actually just try to draw the same thing here. You got this bar here filled with electrons here, this band gap there. But yes, inside here you have like this 2 electrons missing. But then you also have in here like a acceptor level, and then after that you have this other empty side at the top. So that's basically how I would actually draw that. Good. Oh, okay. Huh. Stop it. There we go. Okay. So that's that. Oh, wait, what? Okay, there we go. Certain organic semiconductors follow the same trend of temperature versus conductivity as inorganic semiconductors. A schematic is shown below. What caused the near zero slope of temperature dependence in the intermediate temperature regime? It is because of the doping. Which is basically making it a constant conductivity. Because because of the acceptor level, so that the electrons at the top will just flow, and then it just no, wait, what? If you have the temperature very low, constant conductivity. It is not really the doping, but it has like this constant conductivity from the band gap. I believe so. I don't know if the answer is correct or not, but yes, I am just trying to explain my reasoning. So yeah, I guess that's that. Theoretical studies have shown that polyethylene could exhibit near zero temperature dependence from 100 Kelvin up to about 450 kelvins. However, the glass transition temperature of your polyethylene is near 400 Kelvin. What is one thing you could do to increase the glass transition temperature of your PE semiconductor so that it can use over a wider range of temperature? Cool it faster. Well, basically, when you just cool something faster, it would just basically have have its have its TG to be shifted towards the right side, which would basically help a lot. So that so that's basically how I'll do with that because like yeah, because of the glass stuff. Problem 5. Oh, okay. An alien sword of pure metal has fallen from space onto MIT's campus. As an expert materials scientist, me? No, obviously I'm not really a great material scientist, but yeah, I know the theories. You are called in to investigate its properties. An alien sword, who knows what it's made of? Oh wait, we can find out using X-rays. Yes, we can find it out using X-rays. First things first, let's figure out what crystal structure the material in this sword has. You stick the sword into your X-ray diffraction machine and wait for some results. Unfortunately, the alien sword released a blast of alien energy during the experiment. Not only does it damage your XRD machine, but the results get all ripped up. You manage to salvage some pieces of XRD shown below. Based on the salvaged XRD graph, what are all of the possible cubic crystal structures the sword could have? For the okay, so yeah. So yeah, for the cubic structure, obviously, the first thing that you need to consider first is obviously simple cubic. Because simple cubic could be anything, but yeah, because of this guy is actually shattered, so yeah, there is a chance of it actually being a simple cubic. But also, it could also be a body center cubic because of its, what do you call it? Because of its structure. Wait, what? BCC. Yep. Because of its oh, because when you just sum all of those things up, it is a it is always an even number, not an odd number. Because when it is an odd number, it's not allowed. Third thing, FCC. It couldn't possibly be FCC because for FCC, all of them must be even or all of them must be odd. But but yes, for this one, there are some even and some odd. So yeah, this is not possible. So those are the two things. You still don't know what is the sword is made of. Luckily, the X-ray generator part of your $1 million X-ray XRD machine hasn't been damaged. Undeterred, you decide to make the sword of X-ray by accelerating electrons added to generate an electron spectrum. Draw an X-ray spectrum. Label the horizontal and vertical axes. The Bremsstrahlung radiation K alpha, K beta, L alpha, and L beta. Okay. So yeah, basically this thing is normally something like this here. There we go. I believe this is like 1 over T. This is like the energy there. And so yeah, this guy here is something like that. This is the Bremsstrahlung. And then after that you also get the spikes there. There we go. Ha. And so yeah, basically I believe that this one here is K alpha. And then no, wait, no. Which one is K alpha? Which one is K beta? Alpha is the shorter one, beta is the longer one. Yeah. Oh wait, yeah, this is actually the intensity. This is the intensity. Or the no. It's not the intensity, it's the lambda. This is the lambda, or sometimes the energy. It is pretty much the same thing at this point. So yeah. Which one would actually have the higher one? Is it K beta? Like yeah, K beta actually has the longer one. K alpha has a shorter one. L alpha is a bit more shorter, and no, L beta is shorter. Okay, so I guess this one here would be K beta, and then this one would be K alpha. This would be L beta, and then L alpha. L alpha. Oh wait, no, sorry, this is the lambda. And then this one here is the intensity. Because of my cheat sheet, which I actually just cheat a little bit. I'm so sorry. But yeah, that's basically the XRD. I don't think that I was actually tested again on the Bremsstrahlung because of I'm just actually looking at my notes and I didn't actually do the test on my book. So yeah, I guess that's that. I hope so. That's correct. I think it's correct. I don't know. It might be. Okay, so I guess that would be my answer. The K beta first and then the K alpha, because of my actual knowledge on energy levels. Because like yeah, it's all on dropping. So yeah, basically K beta will actually drop to get yourself like yeah. So like yeah, from the K beta, would it would actually drop like from the energy level from a very higher point, which is a level M to level something. So yeah, and then for L beta it's actually N to L, and so yeah that thing is actually pretty high as well. And so when you actually just consider that into your what do you call it, that EC over lambda, you would you would get some stuffs, I believe. Like yeah, the E and C would be constant anyways, but yeah, the lambda is something that you need to consider, because like with the oh wait no, I think I think my answer is correct, but yeah, who knows. So yeah, I don't want to really actually just to get stuck on that one problem. So yeah, I guess that's yeah, this one here. You can figure out what material your sort is by analyzing its X-ray spectrum. In the resultant X-ray emission spectrum, you observe L alpha peaks at the wavelength of lambda equals to 2.3883 times 10 to the power negative 9 meters. What is the metal the sort is made of? Assume the screening factor sigma for L alpha is 7.4. So we just need to plug the entire numbers in. Oh, we can actually just now try to find what Z is. So yeah, the first thing first is that E equals to HC over lambda. So yeah, basically we can just plug in the entire numbers for the H, which is 8.314. No, it's 1.6022. Wait, what? I forgot. Yeah, because I don't have my table of constants. 13.6 Z minus 7.4 squared. And then like yeah, this one here is from L alpha. So basically yeah, you basically have K, this is subshell 1, and then you got K, JKL, this is 2, and then the third one is M, that's the third peak. And yeah, because we're talking about that, so yeah, this guy would actually drop from this guy to this guy. So yeah, I guess the screen, oh wait no, actually it would just jump up first and then it just jumps down. So I would actually just do this by a quarter minus 1/9. Yeah, because because of its spectrum. So yeah, so we can actually just calculate the Z now. So get out your calculator, because we are going to be counting. I believe the H is 8.314. No, it's 6.626 or 4.136 electron volts. We are actually using electron volts, so yeah. We are going to be using that of 4.136 times 10 to the power of negative 15. multiplied by 3 times 10 to the power of 8, the speed of light. Oh, wait. Times 10 to the power of negative 8. No, 10 to the power of 8. 3 times 10 to the power of 8. Times 3 times 10 to the power of 8. There we go. So 4.136 times 10 to the power of negative 15 multiplied by 3 times. So that would equal to HC, which is 1.2408 times 10 to the power of negative 6. Okay. And then we divide it by the lambda, which is 2.383 times 10 to the power of negative 9. That means that the energy that we have is 520.688 electron volts. We will divide it by 13.6. So we have a 38.2858976. And then after that we want to divide it again by the fraction of 5 over 36 there, and then we will take the square root of the answer 16.6 there, and then you will add it by 7.4, 24. So we can just look into our periodic table of Z of 24, which is chromium. So the answer here is that the Z here would equal to around 24. This would mean chromium, as we have finally found out the material. Very good. Unfortunately, you got so absorbed in your work that you don't notice shooting accelerated electrons at the sword has heated it up. The sword has been 600 kelvins for the 3 hours you spent analyzing your data. In other words, your sword has been annealed. In one sentence, explain how this might change at least 2 mechanical properties of the sword. Well, actually, I don't really know about this, about annealing stuff, but I believe it's all about the structure that will make it brittle and stronger. One sentence, explain how this might change at least 2. Because of the structure, it should change up, or the defects. Yeah, the line defects make it brittle and stronger. So yeah, that's basically that. I have remembered what is annealing. The graph below has a stress strain curve before your experiments. Oh, you have already done that. Draw the stress strain curve for the surf after your experiments, i.e. after it was annealed and has been returned to room temperature. So according to my assumption that it would just have some force, and then after that it's gonna have like this thing, and then it is gonna fracture at some point. That's basically my prediction. Because basically it is made much more stronger. Oh wait, no. This thing means that this would actually have a small elastic regime, but then it's gonna have this crazy plastic deformation pretty high. Because it is much more stronger, but then it is much more easier for it to fracture. So that's why. That's that, I believe so. Okay. Problem 6. Let me just take a drink first. Okay, problem 6. How long has it been? 1 hour. Good. So, yes. You were working in Professor Grossman's lab and have been given the following solutions. Solution 1, 0.0334 grams of calcium fluoride in 2 liters of water. Solution 2, 0.0334 grams of calcium fluorine in 3 liters of water. Solution 3, solution 2 plus 1 liter of 5 times 10 to the power negative 5 lead F2. Assuming the ionic solid is completely dissolved to create a saturated solid, what is the KSP of calcium fluoride in solution 1? Okay. So let's actually just write this first down. That calcium chloride would actually have this equilibrium balance here, turning it into a calcium 2 plus and also 2 F minus. And so the KSP would equal to Ca over Ca plus 2F, yeah. Because like yeah, the CaF2 would actually be placed into another place, but yeah, we can assume this thing to be X. That means that this guy would produce X and 2X. So you're just basically finding this guy to be 4X cubed. Okay, ouch. So we just need to find the first concentration. So what is the concentration of CaF2? So the way that I'm going to be doing this is that you can actually, yeah. You can actually just use the thing straight away. So yeah, let me just plug it in straight to the calculator. 0.334 cubed. No, you don't do that. Instead, you need to divide it by the liters, which will give you 0.167. Okay, there is a storm, so I hope that I won't be disturbed by the storm. And so you just need to cube the answer, multiply the thing by 4 times the answer. So what you'll get here is that the KSP here would be 0.019, let's say. And then what's the units? Well, I am using grams per liter, so the units would be gram cubed liter per liter cubed. Well, yeah. Unfortunately, there's a storm. So I don't know if I can actually just finish this up. Let's hope. Let's hope I can actually just finish this up quickly. 0.019 grams cubed per liter cube. Okay, good. So okay, so now the concentration of solution 2 is 1.43. Okay. The concentration of solution 2 is 1.43 times 10 to the power negative 1 molars, and the KSP of lead F2 is 3.7 times 10 to the power negative 8. What are the concentration of each ion in solution 3? Okay. So for this thing here, this would actually be some sort of an issue because like, yeah, you are having like these two guys here together. And so to calculate this, we need to calculate. Okay, my brain is frozen at this point, so yeah. Okay, so for the one from solution 2, the calcium. Okay, so when you have this, let's just divide it back by 4. You take the root cubed of the answer to get back your 0.167. That is the x. Okay, good. Oh wait, that's the KSP for that particular thing. So my brain has been frozen. Do you need to divide it all by the CaF2? I don't think so, because like, yeah, it's gonna be with water. But yeah, the water would actually cross each other out. So what you have is CaF2. When you got 1.40, oh yeah. Oh yes, actually, yeah, that's true. Because because of the situation, 1.43 of this would mean that the CAQ would have 1.43 times 10 to the power of negative 4, and then for the F, CA2 plus, and then the F minus would equal to 2 times of that would equal to 2.83, 2.86 times 10 to the power of negative 4. And now it's starting to rain. Okay. Yep, this is gonna rain pretty badly, so yeah. I hope I can finish this. Okay, so the lead here. Oh wait, no, never mind, wait. The concentration solution 2 is 1.43 times 10 to the power negative 4. Okay. Wait, really? Okay, never mind. It's still raining. Actually, I know how to calculate for solution 2. So yeah. So yeah, the way for you to actually calculate for let me just erase this guy first. There we go. So okay. And it started raining again. Good. So yeah, we just need to go ahead and just try to calculate how many moles are there of CaF2 inside that thing, because I am obviously really wanted to turn it into molars, because that, yeah, what we have there is actually molars. So 0.0334 of that. Oh great, it's still raining. I guess so. So 0.0334 there needs to be divided by the MR, which is for calcium it's 40.078. Why is it raining right now, man? Why? Grr. Wait, I cannot do that then. Yeah, the fact that I can actually do that because like, yeah, the grams would actually be different. So I guess I need to find a different way to solve this thing. Well, actually, it's possible. Anyways, you added by 2 times the MR of fluorine, just 18.9984. So that would equal to 4. Let's just write this guy down. So this guy here has 4.28 times 10 to the power of negative 4 initially. And so when you just plug it into this formula here, you just need to divide the answer by 2 to get yourself the thing, and then you take the cube to get the answer there, multiply that by 4, you'll get the real answer, which is a very small number. It is in fact a very small number. So the KSP here would be 3.92 times 10 to the power of negative 15, negative 11 moles cubed. I guess that's the... No. Yeah, never mind. It's correct. It's moles cubed. And so with this, I think I need to persist. Okay. The concentration of solution 2 is 1.43 times 10 to the power negative 4 molars and the KSP of lead F2. So yeah, we just need to calculate the concentration, which means that we know that CaF2 would actually transform into Ca2 plus 2F minus, and then this guy here actually has 4.28. Okay, the concentration of solution 2 is, well, that means that this is the KSP, isn't it? I think that's the KSP, but no, I think that's the X. Yeah, that would be the X. So yeah, basically from that number that you have, which the one at the top there, you divide it by 3 to get yourself the moles, which is 1.42. Oh, okay, yeah, that's that. So basically what you'll have is actually something. Assume the ionic solid is completely dissolves to create a standard. Because this guy actually completely dissolves, so yeah, I would say that yeah, this guy would basically be the same, having 1.43 times 10 to the power of negative 4. It starts raining again. No, please, focus. Here we go. Come on, you can do this. And so, wait, wait, am I doing this correctly? When you have x there, so yeah, you can actually just multiply that thing. So yeah, yeah, it's correct. And then you have 2.86 times 10 to the power negative 4 moles of that. And then for lead, F2 what actually deforms into lead 2 plus and also 2F minus, but then the answer would be 3.7 times 10 to the power negative 8. So when you just first plug in that 5 times 10 to the power negative 5, ouch, 5 times 10 to the power negative 5, I still don't know how to calculate this. You know what, 5 times 10 to the power negative 5 moles equal to 5 times 10 to the power negative 5, and then, oh wait, no, sorry, this guy here would actually be, this guy here is not actually that. Instead, you will actually have like this x. So this one here would be subtracted by x, while this guy have x, and this guy here has 2x. So we just need to solve this problem. This is gonna take a while. So we know that 3.7 times 10 to the power of negative 8 would equal to those things, which is x squared. No, sorry. 4x cubed over. Oh wait, you also have the over. This thing, this entire thing is over x. So this is just 4x squared, I guess. Because like yeah, for KSP it's just basically, yeah, Wait, no. But you are talking about solids, so yeah, you don't. So yeah, you don't really need to care about that. So yeah, because like yeah, basically for solids you don't have concentrations normally. So yeah, it's still fine. So yeah, you will have this 4x cubed. But then yeah, this guy here doesn't. That guy there doesn't really matter because it would become less solid, but it's still solid, so we don't really need to care. So when you have that, you could calculate how much x that would be. So, so when you have that 3.7 times 10 to the power of negative 8, you divide it by 4. Oh, whoops. That is not what I meant. Divide it by 4. There we go. You'll get 9.25 times 10 to the power of negative 9. And then you'll take the cube root of your answer. It would be around 2.1. So x would equal to 2.1 times 10 to the power of negative 3 m. Good. So let's just write this guy down just by typing because this is too much. So yeah, Ca 2 plus would equal to 1.43 times 10 to the power of negative 4 moles. And then for the lead 2 plus, that would equal to the one that I've calculated, 2.1 times 10 to the power of negative 3 moles. But then you need to calculate this last guy here using some crazy technique, which is mv equals to mv, obviously. So because like yeah, because what we're doing is just to try to find the number of moles. So yeah, let's just go ahead and just try to find what this f minus here. So yeah, the first thing here is that we have this 2x there, which is 2 times that guy there. So we have a 4.2 times 10 to the power of negative 3 concentration of f minus inside that 1 liter. So you just need to multiply that by 1, which is basically nonsense. Yeah, it's basically nonsense. And then after that you need to add it by the concentration of 2.86 times 10 to the power of negative 4. That is from the second solution. You need to multiply this by 2 because that's the volume. To get a total of 4.772 moles, you divide it all by 3 to get the concentration, which is in here 1.59 times 10 to the power of negative 3 moles. So that's the answer. Good. Finally. Write out the KSP for both CaF2 and lead F2. Okay. This one would be easy. For the CaF2 that will be Ca2 plus and also F minus squared. For the KSP of the lead, it's pretty similar. Lead 2 plus with the fluorine minus squared. Good. Let's see. How long has this been? 1 hour and 30 minutes. Good. Use the expression from BII to show why there wouldn't be any precipitations. What? Show why. It would be very small. But yeah, when it's like negative. Wait. When the KSP is negative, that means it would favor the bottom side, isn't it? Wait, what? Wait, what? I don't understand. Here's to show why there wouldn't be any precipitates. Uh, Small number, I guess. Because like the molarity is actually pretty small. So yeah, I would say that yeah, it would have a oh, small number meaning no precipitation. Hey, there we go. I did entire maths, which I know that it's not correct. Wait. Wait. When you just plug in the... Jeez. This is much more harder than I thought. Because of one thing. Because when you just put CAF2, and then after that you just... And then you introduce that like F2, this would instead actually have something else, which is 2x minus that other guy. Which is that? Which is the one that I've already found. Okay, good. At least it works. Good. So yeah, small number, no precipitations. Because of some, I don't know, weird maths. But yeah, it should be like a bigger number, a much more precipitation. Bigger number, precipitation. Like yeah, it is pretty weird. Because look at that. This thing here is something that I don't really understand. Oh well. I guess I might have a mistake there. Anyways, let's go to the next one. Now consider solution 2 alone. You want to precipitate the CaF2 out of solution using one of the following chemicals in your lab. Lead, lead I2, CaS, and MgF2. Name one chemical you could use to precipitate CaF2. The way for you to actually to do this might be to use MgF2 or CaS. Because like yeah. Because yeah, just by using that, you would actually just change the things. But yeah, I would say using MgF2 would actually be much more better because like yeah, it is gonna be transforming that much more quickly. How many moles of the chemicals that you chose for part C I is necessary to precipitate the original 4.28 times 10 to the power negative 4 moles of CaF2 out of the chlorine? Wait. Oh wow. That's that is the thing that I'm gonna be doing. To precipitate the original for okay. How many moles are necessary to do that? Unfortunately, I don't know. Because CaF2 okay, so we are just assuming that KSP would be that. So that means that the entire thing that I have done is actually wrong. Congratulations. But you know what? At this point, I don't really care. How many moles of the chemicals that you chose for part C I are necessary to precipitate the original 4.28 of calcium fluoride out of the solution? Unfortunately, I don't know. If you want to do this, this is just basically the common ion effect. But then, yeah. In order to do this, you need to have that other F2 minus to be increasing so that the calcium would decrease, which means that you need to do the precipitation. So yeah, I would actually just I won't answer because like yeah, this is something pretty hard for me to actually to think about because like yeah, I am not really that good at aqueous solids like the equilibrium and such. But yeah, I'm gonna try my best to actually to try to find a different way to find this solution. Great meme. Buy CAF2, synthesize CAF2, calculate chaos B to precipitate CAF2 out of solution. Wow. So yeah, I guess I will later need to try to figure this out because at this point my brain is very small. Okay, good. Problem 7, 25 points. Above are sketches from 3 different textbooks of 3 samples of silicon oxide. One of the samples contain Na2O as a network modifier. Which sample contains Na2O? Obviously it's I. Simple. Because like yeah, you got like this random spots of reds. And it is also splitted up, so yeah. Which sample is crystalline quartz? It's obviously I. Plot your molar volume to same time, be sure to label your axes. Okay. For this stuff here, it's actually pretty simple. That's T. This one here is V per mole. And so yeah, you basically have this. You have this like part 1 stuff there. That would be Tm. No, sorry. It should be something like this. There we go. And then you got like these stuffs here. This would be your scission stuff. Wait. Which one would pack much more easily? If you want to decrease the stuff. So yeah, this guy would be the scission. This would be I. This one side would be I. This side here would be TG1 and TG2. This one here is TG2. So yeah, I guess that's that. Okay. Like yeah, I am not actually giving up, but yeah, that's how I do it. Okay, let's see. Okay. Na2O and CaO are both network modifiers. Network modifiers are added when the glass is in a liquid state. You know that the rate law of dissolution of CaO in liquid silica is rate CaO equals to 4 times CaO. Write a similar rate law for the dissolution of Na2O in liquid silica and use it to fill in the following table. The Na2O reaction is second order in terms of Na2O and independent of the silica concentration. Please determine the value of the rate constant and write the units of Na2O and rate. Okay. So this guy here is obviously molars per second. And here I'll use molars. Okay, it's fine. So yeah. This guy here is actually transformed by 2. That means that this guy here must be 4.8 times 4. That's basically how you actually solve this problem, because again this is a second order term, so yeah. So the rate law here would be K, a constant, and then the concentration of Na2O squared. Simple, right? And then what are the units of the constant? So yeah, the first one there is actually a first order one, so yeah, it would be only per second. But then for the Na2O, that's 1 over ms. That's that. Taking about the size of Na versus Ca, explain in one sentence why it makes sense that sodium oxide reaction occurs at a faster rate than the calcium oxide reaction. Ooh. Thinking about the size, explain one. I guess of its smaller size. Like yeah, because because of the smaller size that yeah. Because of smaller size. it would work like that. So yeah, smaller size, and then also it's uh, and its bond strength as well. So yeah, that's how I think. That's how that's how I think that should work. Okay, three more problems. You are interested in understanding the diffusion of hydrogen gas through palladium. Filter to make sure the concentration of H doesn't get too high in the living quarters of the rocket. Modify it as you're not sleeping. Original image is in the public domain. Source NASA. Calculate the original number of lead vacancies in 1 mole sample of lead, assuming the vacancy activation energy 0.7 electron volts, T is 300 Kelvin, and the entropic constant is A equals to 1. So the vacancy would be okay. So yeah, basically this is Svante. So you know what the fraction is. The fraction of this would equal to the A, which is that e to the power of negative A, negative 0.7, divided by the kBt. But then we are using moles, so we are using R. That's how we do it. Oh, there we go. So you plug it into your calculator to find out what this number is. E to the power of negative 0.7 divided by 8.314 divided by the temperature 300 Kelvin, you'll get like around the fraction of it is actually 0.99971. So that's a lot of vacancies. That's that's a very big amount of vacancies. That fraction. It is pretty near 1. So I think I might have done something wrong. Like, you know what? I'm gonna do this, divide it again by 6.8 times 10 to the power 23. 0, good. That is exactly what I want. Because what I'm using is kBt. E to the power negative 0.7 multiplied by 300 there. Oh yeah, that 300 there, and then the 8.314 divided by 6.02 times 10 to the negative 23. Oh, divide. 1. The math makes much more nonsense. But wait, this is actually multiply. Wait, yeah. Because when you do divide and then you do not divide inside the thing, so yeah. Wait, what? Let's put them inside the cage. Still 0. Good. Somehow I cannot engineer a way to make sure that this die is not 0. In a mole sample, assuming the energy is 0.7 electron volts. Oh. So now I need to modify this guy. Okay. So 1 joule is 1.6022 stuff times 10. Yeah, one electron volt is 1.6022, so yeah, we just need to divide it again. After all this time, the thing is still at joules. Oh wow. But then, so that means that I need to divide this number again by this weird other number, which is 1.6022 times 10 to the power 19, and still 0. Should I just cage it in? I think I should. Wait, the joules is at the bottom. So yeah, the sign should be correct. It should be divided. What? I still don't understand why. 6.02 divided, that's the kBt. Oh wait, no, this guy's times then. So that's the NA. So, wait. So you got the R, and then you got the kBt. No, you got the kB, but then you want to transform it into another form, which still makes it 0. Huh. So yeah, this guy here should be kBt. Anyways. Okay. So the units would be joules per atom Kelvin, but then I want to transform the joules. So you need to divide it by the 1.602. Oh wow, this would be R divided by NA. The entire thing needs to be divided again by the 1.602. Oh my, oh wow. This is gonna take a while. And then after that you divide the entire thing by 300 kelvins. And you still got 0. You know what? I think I know what to do. I just need to write them all. The entropic constant is 1. E to the power of negative 0.7 electron volts. Or we can just actually transform this first. So instead of actually doing this crazy thing, we can just plug the 1.602 at the very front, just to transform that to its stuff, negative 19, divided by the crazy answer that you got there. And so the units would be at joules. Oh wait. Oh wait, that's why. That's why it makes sense now. Okay. Let's do this thing again. E to the power of negative 0.7 divided by the kb, which is 8.314, divided by the 6.02 times 10 to the power 23. Okay, and then after that, what to do next? I need to divide this bottom value here by 1.602 times 10 to the power of negative 19 R. And then after that, divide it by 300. That would be there we go. let's see. Okay. Okay. I found a fraction. Good. We just need to multiply that by 6.02 times 10 to the power 23. 1.056 times 10 to the power of 12. Oh wow. That took me a while to find the vacancies. Great. And yeah, unfortunately I need to go a bit soon, so yeah. The human So yes, I think I will be continuing the stream later on, so yeah. I guess I'll just stop here first because it has been around that many hours. 1 hour and 45 minutes. So yes, I will later just do another stream after this, pretty much at midnight. So yeah, I will be seeing you guys soon. So yeah, thank you very much for actually watching the stream, and yeah, stay tuned for the next stream. So yeah, I will just need to edit this first to LiveWork 1. So let me just edit this first. Okay. Oh, you know what? I will. Oh, you know what? I will just actually just end the stream first. So yeah, thank you very much, and we'll see you guys later.